Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Chris Smith. What's new in the world of science for you?
Well, it's been a very fertile week this week, actually, and something which is close to my heart is, as a doctor, the subject of heart disease, because this accounts for the deaths of about one person in every three across the whole planet, coronary artery disease. So if we can understand more about how to put right the damage done to a broken heart, perhaps even make a broken heart mend itself, that would be a very wonderful thing. And there are a couple of papers in the journal Nature this week which do take a step towards giving us some insights as to how that might happen. And it's intriguing because this is work done in zebrafish. Now, zebrafish are really tiny little animals, and they're almost transparent, so you can put them under a microscope and see straight through them, and this makes it very easy to study them, and researchers have found all kinds of interesting things out this way. And because zebrafish contain many of the same genes and developmental pathways that we do, if you find what's going on in this very simple organism first, you can then scale it up to study the same system in the human once you know what you're looking for. So it makes life a lot easier. And two groups, one is Chris Jopling and the other Kazu Kikuchi. They've both got papers in Nature this week. They have described what happens if you damage the heart of a zebrafish. Now, if you do this to a human, if you damage the heart, what tends to happen is that the heart will, A, not regenerate the damaged area, and B, it will form a scar where you damaged it. Neither of which are good news for heart repair. If you do the same thing in these fish, though, the heart completely regenerates. In fact, you can remove 20% of the ventricle, the pumping bit of the heart, and it will completely regrow. So that says, well, if these fish know how to do this, it might be possible to turn on the same process in a human, and we can put our own hearts right too. And what they've discovered by doing these lesions, this damage to zebrafish hearts, is that the heart muscle cells themselves, they do what's called de-differentiate. So they despecialise, they stop being muscle cells for a while, they flock to the area which has had the damage, and then they grow many, many more muscle cells. That's the first thing, and that plugs the gap. And then they electrically wire themselves back in with all the other muscle cells in the heart so that the electrical rhythm is restored. And they've found a few genes which seem to be linked to this growth process. One of them is called GATA4, G-A-T-A-4, which is also expressed in embryonic fish in order to make the heart in the first place. And so by understanding these pathways and understanding how these cells are doing this gives us enormous insights into how we might be able to make the same thing happen in humans.
It's time to start our science questions. Our first one comes from the email from Lane Larson, who says, exactly why do men have nipples? Dr. Chris, solve that one for us.
Indeed, they don't do any breastfeeding, not normally anyway, amongst humans. So why have them? Well, they actually are a developmental remnant. What I mean by that is that they begin to form when we're in utero, when we're a little baby, which is forming inside the mother, and they form under the influence of genes which dictate which bit of the body should develop into what. So when the body develops, it starts off as a flat plate of cells, and that flat plate of cells, which is only very tiny, rolls up into a tube, and because there's already another plate of cells inside, that also rolls up inside the other rolled up tube, so you get two tubes, one inside the other, and that's why you've got a tube which goes from your mouth down to the root end, and that's your gut tube, and then the outer tube is the skin round the outside. Now, the interesting thing is that when the body rolls up like that, it has what's called a neuraxis. It knows what's the head end and what's the tail end. And the body develops as a series of segments. So there are different genetic programs being executed at different levels down those segments. So if you imagine taking that tube and slicing it up into a series of segments, as if you've got a Swiss roll and you're cutting bits off of it, different genes are being run in different segments. So each of those segments has a unique identity, genetically speaking, and those genes tell it to develop a certain way. So that's how it knows where to put the arms, where to put the nipples, where to put the legs, and so on. Now, because male babies and girl babies, early on in development, when this patterning process is happening, are identical, because what's called the gonad is indifferent at that stage. You can't tell the difference because the ovaries and the testicles develop inside the abdomen, both in the same place, and it's only later that they migrate to their final positions. Early on in development, there is no difference between the boys and the girls, and therefore the genetic program that makes the nipples makes the skin make the nipples anyway, but it's only later on in development, when there's more estrogen around, when a girl goes through puberty, that in response to that estrogen, the nipples get bigger and the breast tissue develops, and that gives breasts. But it's not true to say men can't breastfeed, and nor is it true to say that the males of all species don't breastfeed, because if you give the right cocktail of hormones and nipple stimulation to a male, a man can produce some milk from the breast, and some drugs have as a side effect what's called galactorrhea. You actually accidentally start to produce breast milk, and this is a side effect of certain drugs that can affect certain parts of the nervous system and its function. And there are some bat species, there's a bat called the Dayak bat, where the male does actually breastfeed the young bats. I think it takes part in about 20% of the breastfeeding duties. So that's a male that really does get stuck in and help. Doesn't change nappies, though, but then I don't think bats wear those.
All right, let's go to our next question, and let's welcome onto the programme Les. Hello, Les.
Hello.
Hello there. What's your question for Dr. Chris?
Well, I noticed Cheryl Cole, singer, has a definite accent, but it doesn't seem to come through on any of the songs that I've heard her singing. Why?
Chris?
The reason for this is because accents are learned, and the evidence for that is that if you look at someone who is born in one country, then they go to another country and they grow up there, they'll have a mixture of accents, but they learn to speak like the people they're around. And that shows that humans are very, very adaptable, and we take on and embrace what's around us in order to fit in, because being tribal and being social species, we try to match everybody else, fit in with everybody else, and that means that we're more likely to be accepted by everybody else. Now, singing is also something you learn. And so you learn to speak one way, but you also sing in a way that sounds good. And in singing, you accent things slightly differently to make the music sound good. It's not a vocal music in the sense that you're speaking and making a musical riff, if you like. So it's because people are learning to sing a certain way and emphasising different aspects that you don't notice those same intonations and changes which you do when someone's speaking.
That sounds fair enough. Well, thank you very much.
Thank you very much,
Yeah,
Les.
bye.
Thank you. Bye-bye. Our next question comes from Agnes in Braintree. She says, my daughter was recently diagnosed with Meniere's disease. I've never heard of it and wondered if you could tell me a little bit about it. Chris?
Yes, well, Agnes, Meniere's disease affects the ears, and it's caused by a lack of fluid in the ears, and this can affect both hearing and also balance. Because the ear, the bit of the ear that converts sound waves into brain waves, the cochlea, contains fluid, and so do the balance organs, the vestibular system, which enables you to balance your body and match movements of the body with your eyes so that you can look at things and keep a steady gaze. So the vestibular system is a series of little circular canals. They're a bit smaller than a 5-pence piece, each of them. They're very, very small. There are 3 of them, and they're arranged at 90 degrees to each other. So there's one of them which loops from front to back. So if you imagine a giant sort of one of those discs that you can throw, if you had one of those and you held it up so it was a ring side onto your head, that would be the same as one of these canals. If you then tilted that disc 90 degrees so it was horizontally 90 degrees like a giant halo, that would be equivalent to another one of these semicircular canals. And then if you had it so that you twisted it 90 degrees up in the air from a halo position, so it was going from one ear towards the other ear, that would be the orientation of the 3rd canal. So in other words, you've got one of these little canals pointing in every single direction that you could move in 3 dimensions. And inside those canals is fluid. And the fluid brushes against tiny hairs that project into the canal's interior. And when you move your head, whichever movement you make, the bone moves a bit, but the fluid initially stays still. It's a bit like if you have a glass of water and you twist the glass, you'll see that there's a lag between the glass moving and then the water catching up. And as that happens, this presses on these tiny hairs inside the canal, and it triggers the hairs to fire off nerve impulses into the brain, and the brain decodes the contribution of each of those different canals, and it can work out, therefore, how much you've moved in any one direction. And that tells the body how to change your musculature to balance you, and it also connects to all of the motor nerves that control your eyes so that your eye movements directly equal and oppose the movements of your body so that your eyes stay staring at the same thing even though your body's moving. And that's why you can do this on yourself. If you hold your finger out in front of you and shake your head from left to right, you'll notice that you can keep on looking straight at your finger without any interruption of the vision. But if you shake your finger very, very fast, you can't keep up with your eyes. So your eyes are being able to respond to body movements and match those to maintain a good, solid, conjugate gaze. The ear is also affected, the hearing, because the lack of fluid can impact on the ability of the tiny bones in the middle ear to put the sound waves into the cochlea, and therefore it can struggle to actually turn those sound waves into brain waves. And so both hearing can be affected, but balance especially. And what people tend to say is when they've got Meniere's disease is that it can come and go. They can get periods when it's very bad and periods when it's less bad, and it tends to be associated with dizziness, and people may have to lay down because every movement can be misinterpreted or overinterpreted by the brain because the signals are getting disrupted because the fluid levels are wrong. And as a result, it can make people feel quite sick sometimes. So there can be hearing consequences and balance consequences, but luckily there are some drugs that can make people feel a bit better.
Thank you for that, Chris. Now, we go once again to the phones. We've got Stuart on the line from Southend. Hello, Stuart.
Hello.
Hello, you're through to Dr. Chris. What's your question?
Yes, I'm a keen golfer, and I play quite often on links golf courses, which are courses by the sea. And something that's always intrigued me is that obviously the wind is a major factor, being so close to the sea, but quite often the wind will not get up to about 9 o'clock in the morning, and then about 5 o'clock in the evening it dies down again. But it doesn't seem to be tide-related, and I wondered the reason for this.
Hello, Stuart.
Hello.
Well, there is the concept of a sea breeze, which you've probably heard of, and it sounds like it's sort of folklore, but it's real. And what happens is that when the sun shines down on the Earth, the sun hits the Earth and it also hits the sea. The Earth warms up quite quickly, and the sea warms up much more slowly because the ability of the ocean to soak up energy is much bigger than the land surface. So what that means is over the course of a day, the land gets warmer and warmer and warmer, but the water stays similar, about the same temperature, maybe a little bit more.
Right.
And as a result, air starts to rise quite quickly off of the land surface because warm air rises. The land surface is warm, it transmits some of that heat into the overlying air, and this pushes the air up in the air. With me so far?
Yes, yes.
The air therefore comes in off the sea because that's colder and displaces the rising air. And therefore you end up with a sea breeze. So these things tend to happen more towards the end of the day when the sun has baked the ground all day, warmed it up and got the air rising off the land, and therefore the cold air comes in to displace it.
That explains it very well. Thank you.
Thank you.
Bye.
Bye-bye. Now, Mike in Colchester says, watching the birds, if we drink putrid water, we get ill. Birds, however, bathe in it and drink in it and don't seem to have any problems at all. Why is this?
I think it depends on what sorts of microorganisms are in the putrid water. This was put actually very well by someone on the Naked Scientist forum recently, who was making the point that, because one of our questions that we're looking at this week is what is worse, to be bitten by a human or bitten by a dog? One person pointed out in response to that question that the kind of bugs that live in a dog mouth may not necessarily be well adapted or able to grow very well in a human. But all human bugs, by definition, if they're in a human, know how to grow quite well in a human, and therefore a human bite may be worse for the simple reason that you're being infected with potential pathogens that are already well adapted to humans. So if you extrapolate that to putrid water, if the water is putrid because it's contaminated with human waste, then it could well contain bugs and other viruses which are well adapted to humans because they've come from humans. Therefore, it's more of a threat to you. On the other hand, if the putrid water is just nasty because it's got something in it which actually is not bad for you because it's an organism which is not going to affect you very much, some mould or fungus or something, then as long as that hasn't secreted something into the water to which you're sensitive, then you could probably drink it. And the same is probably true for birds. I suspect that because the water may look a bit manky, just because it's got some weed and other stuff growing in it, doesn't necessarily mean that it's got toxins in it or any bacteria that are going to make the birds ill. If, on the other hand, the birds began to drink water that other birds had fouled, then it's possible they could pick up bugs and nasties from that.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Right, our next question then comes from another Mike who says, painkillers, how do they work and how do they know which areas of the body are in pain? Do you know, I've always wondered that. Chris?
It does seem rather strange, doesn't it? You have a headache or toothache or something, you take some paracetamol and it goes away, and you think, how does the drug know which bit of the body is affected and therefore where to home in on? The answer is, it doesn't. It's actually a global effect. The way these painkillers work, and we can use aspirin as a good example. Aspirin is a non-steroidal anti-inflammatory drug, NSAID. And the way it works is that it inhibits an inflammatory process which gives rise to chemicals called prostaglandins. And these are made by an enzyme called cyclooxygenase, COX. And the aspirin molecule locks onto this enzyme and irreversibly blocks it. So it stops the enzyme working. Now, as a result, this enzyme cannot make any of these prostaglandins, which are inflammatory. So if you have an area of the body which is inflamed or has ongoing inflammation in it, if you take some aspirin, the aspirin goes to all of the tissues in the body, and wherever there are these enzymes, these cyclooxygenases, the aspirin will block them. As a result of the aspirin blocking them, any ability in that part of the body to make many of these prostaglandin molecules is reduced. So if there is some inflammation there, even though it remains inflamed because there's some cause of inflammation, the amount of the inflammatory chemicals begins to drop because the body can't make them locally there anymore, and therefore the amount that they wind up the nervous system or stimulate the nervous system, triggering the sensation of pain, drops, and therefore you get relief. But that's why when the drug effect wears off, because the body makes more of the enzyme to make up for the fact that aspirin has inhibited it permanently, and that's why the pain comes back again, because then you start to resynthesize or remake these inflammatory chemicals, and that's when you need to take some more aspirin.
Now, our next question is again on the telephone. Hello to Tony.
Oh, good evening.
Hi, how are you, Tony? It's always a joy to have you on the programme.
And it's always a joy to talk to you, dear.
What's your question for Chris?
It's about rainbows. Why are they the shape they are?
Chris?
The reason rainbows happen is because it is a trick of the light. Of course, a rainbow doesn't really exist. There's nothing there. But what you need, what the recipe for a rainbow is a dark background, in other words, a cloudy sky, and a nice, brilliant sunshine coming from the other direction.
Yeah.
So what you need is that cloudy, dark sky to be spitting out some rain.
Yeah.
The sunlight goes into the rain particles, so you have little raindrops. The light goes in the front of the raindrop. It bounces off the back of the raindrop, and then comes back out the front. But different wavelengths of light get bent by different amounts. So red light gets bent more than blue light, I think. Might be the other way around. But anyway, what that means is that the white light from the sun, which, as Isaac Newton showed with his prism experiments, is a mixture of lots of different colours all mixed together and making it look white, that white light gets split up, just like a prism, by the raindrop and reflected back at you. And because you see these different light rays coming at you from slightly different angles, what you see is a rainbow because you're seeing them all split up. And because the raindrop is round, it's beaming you back a circle of light, but you can only see half of it because the other half has gone below the horizon.
So it's not from where it's coming from, it's the actual raindrop that's making the bow.
Yes. Now you might ask, well, what makes the second rainbow? Because sometimes you see two. And the answer to that is that when the light ray goes into the raindrop, it bounces off the back of the raindrop like a mirror, comes back towards the front of the raindrop. Some of the light comes out the front and comes back to your eye, but some of the light gets bounced back again and does another journey inside the raindrop, back off the back surface and back out again, bending the light even more in the process and reversing the sequence of colours. So then you see the second rainbow, but the colours are reversed.
Good
And so
Lord,
that's why
I've
it's also weaker than the first one, darker, because obviously less light is now coming
Yeah.
back to you, and so it looks darker.
Thank you very much.
You're welcome, Tony. Thank you. Bye-bye.
Bye.
Right now, let's answer Billy's question. Well, Chris can. Dr. Chris, what does make a boomerang come back?
Yes, well, boomerangs are a fantastic demonstration of the science of physics, aren't they? Just for anyone who's not in the know, a boomerang is usually a curved bit of wood, and usually it's shaped in such a way as to have two arms which have a curved surface to them. And when you throw them, they in fact behave a bit like an aeroplane, because the air travelling over the moving arms creates a bit of lift, in the same way that an aeroplane wing generates a bit of lift. And so this elevates the boomerang, causing it to gain height. It's spinning, though, so it's not quite as simple as an aeroplane, because aeroplane wings move horizontally, and therefore the lift that they generate is relatively stable and constant. With a boomerang, because it's spinning, it's actually creating lift and torque. Torque means there's a twist force on it. And so the lift that it generates is directed towards the centre of the circle in which it's spinning, and the torque means that it's trying to turn as well in a big circle all the time. And so the boomerang goes up, converting all of the energy you've given it and in the spin into upward lift until it reaches a maximum height. Then it starts coming down, following that torque angle until it returns to you, expending the energy that you gave it to start with and turned into potential energy at height as it turns it back into kinetic energy as it returns. So that, in a nutshell, is a boomerang.
Excellent. I've often wondered that. Now then, let's go to the email. This is from Anne, and she says, what is the difference between the two body scanners, and what do the different types of scans show up? Chris?
Well, there are several kinds of scanners, actually, so it's probably a bit simplistic to say just two. There are MRI scanners, they're magnetic resonance imaging scanners. These use a very powerful magnetic field. The way they work is that when the body goes into a very powerful magnetic field, it makes the spin on all of the hydrogen atoms in the body. In other words, where all the water is, because most of the hydrogen in the body is water and sugars and things. Mm-hmm. But most of the water, therefore the hydrogen is in water, and it lines up with the magnetic field. If you then fire a radio wave through a different slice of the body, or if you fire a radio wave through one bit of the body, this temporarily perturbs all those hydrogen atoms that have lined themselves up nicely, and they then flick back in line with the magnetic field, and as they do so, they give out another signal of their own. They give out another radio wave signal that the scanner can pick up, and by doing this lots of times and monitoring how the hydrogen responds and how the signals arrive back at the detector, you can build up a very, very detailed three-dimensional picture of what's going on inside the body. So this is a very, very powerful imaging system, and scientists are now working out ways to image various different tissues better with it, because you can adjust the way in which you do the scans in order to see certain tissues better than others. And so if depending upon what you want to see, you can set up the scanner slightly differently. So that's how MRI works. There's also CT, which is computer-aided tomography, CT for short, and this uses X-rays. So this is an ionising radiation scan, and this is similar though, because what you're doing is putting someone in a scanner and it fires X-rays from many different directions through 360 degrees through the body, and then looks at what the signal coming through from all these different directions looks like to the detector. And by doing some very clever mathematics, it can work out, based on the different amount of X-ray absorption coming through all the different slices of the body from different directions, what the internal structure of the body must look like, and so it gives you an internal body profile. The downside of CT is that it involves X-rays, radiation. It therefore carries a risk of any ionising radiation, which is that it could damage DNA, and therefore if you had lots of CT scans, you're going to elevate your risk of cancer. But it is very good for looking at certain types of diseases or certain types of structural problems. It's very good for seeing blood if you've had a stroke, for example, or damage to the brain. It's very good at seeing that. So it's a very quick, very effective and very, very reliable diagnostic system. There are other ways to scan people, though, and never forget ultrasound, which is an amazing scanning modality. It's fairly low cost. It is operator dependent. You need someone who's good with an ultrasound probe, but it's still amazing what you can do because it's totally harm-free as far as we know. This sends very high-frequency sound waves from a probe into the tissue, and in the same way as you can work out what a room looks like if you close your eyes and shout in different directions and listen to the echo, that's basically what a bat does to fly around, because it uses echolocation, or a submariner underwater using sonar. It does exactly the same thing with ultrasound, listening for the echoes coming back off different tissues under the surface of the skin. And so you can use ultrasound to look at many, many structures and take samples or do biopsies and things. So it's a very, very safe and very effective and cheap, low-cost way to image things, including developing babies. So most of the scanning done on babies, because you don't want to expose those to X-rays, for example, is done with ultrasound.
Excellent. All right, well, let's go to our phones once again. We've got Alan on the line. Hello, Alan.
Hello, Sue.
What's your question for Chris?
I've been told I could ask two.
Ooh.
One is, again, Harvey Painkillers. Just recently, they've been on advertising, targets pain better than anything else because it targets this and it goes straight to that pain and not to another pain and all this sort of thing. How correct is that, please?
Well, I think to a certain extent this is marketing hype, in the sense that you're hitting pain where it hurts and all that kind of thing.
Yep.
What they're basically saying is that you're going to make the pain better, but the agent is not discriminating in favour of any particular body part. It is inhibiting the production of those inflammatory chemicals wherever the body is trying to make them. Now, in one respect, the body is only really trying to make many of them where there is lots of inflammation going on, and therefore you could argue that in some respects they are targeting the pain. But that's not because there's anything special about the drug. The drug just goes to everywhere in the body, and where it finds something to inhibit, it'll inhibit it. In other words, one of those enzymes that makes the inflammatory chemicals. So they're not actually directing any of the pain-killing effect to any specific part of the body. When you have a local anaesthetic, on the other hand, that does, because what you're doing with a local anaesthetic is you are rendering anaesthetic insensitive the nerve fibres in that area, and therefore you can't feel anything.
That sounds brilliant. Inside the nose, there's a sensitive area that normally makes your eyes water like hell. Does he know anything about that? What it is that triggers
your
that?
nose tissue is very, very sensitive. And the reason that when you pluck a hair from your nostril, your eyes water is because you're stimulating nerves, which there's a sort of neurological reflex that goes from your nose to your eyes and that part of the face, which makes you blink and squeeze your eyes together when you stimulate them. And I think it's partly a defensive mechanism, actually. If something were to go in the nose or you had an irritation there, it's to alert you to the fact that, oh, this is a dangerous bit of my body because something could go in here and then get into my throat, or I could breathe in a foreign object or something. So you tend to guard that area quite carefully. And of course the nose is very sensitive for other reasons, which is that it's being used as a chemical detector in order to sniff out danger around you or food and other people, and also to alert you to how warm and cold things are. So the nose is a very, very sensitive organ, so it's not surprising it makes your eyes water a bit if you treat it badly.
All right, Alan, thank you very much indeed. Bye-bye. Right, and Francis says her husband is diabetic and recently has been getting very bad night cramps in his legs. Is this caused by the diabetes, and is there anything that could be done to prevent this? Chris?
Yes, hello, Francis. It could be, because one of the manifestations or consequences of diabetes is that it can damage blood vessels. Diabetes is a risk factor for the process called atherosclerosis, which is where blood vessels fur up. And people with diabetes can get arteriosclerosis. The arteries can become really quite hard and firm. And this means that they may go into spasm, sometimes at night, and this can starve the tissue downstream of the obstruction or the spasming part of the vessel, and this makes the tissue hurt in the same way that when the coronary blood vessels supplying the heart go into spasm, they can make you have chest pain, angina. You can get the same sort of thing, and a cramp down in the distal extremities, and it tends to affect the distal extremities because the blood vessels there have got the furthest distance to get to away from the heart, and therefore the pressure by the time you get right the way down to the end of the legs in a furred up vessel can be quite low, and this is quite a common complaint, and it certainly gets more common as you get older. It's also aggravated by things like smoking and high cholesterol and high blood pressure. There is some relief to be had by taking quinine, the same stuff that's in tonic water and what's used to treat malaria occasionally. And so quinine tablets can be taken at night time, and they do anecdotally have some benefits on cramps.
Excellent. Let's go to the phones now because Alan is there in Orpington. Hello there. What's your question for Dr. Chris?
When any archaeologist wants to get any information, they have to dig down in the earth. That seems logical. But how comes that the further down you go, the more back in time you go. Does that mean that over time, layers and layers and layers of Earth are coming back on top? And if they are, where are they coming from?
Good question.
Yeah, good question, Alan. And the answer is, yeah, there's a combination of factors. One is that ground may sink a little bit in some cases and be filled in on top. The other is that the Earth is not static. And if you look at the Sahara Desert, for example, it wasn't always a desert. There weren't all those sand dunes there. There were people living in what is now desert on a fertile oasis. They had lots of water from the Nile and they had a wonderful existence. The pyramids weren't always in the desert. All that sand that's come in has blown in since and built up. So the answer is, yeah, when people build things, they build them on top of other things, and other dirt and debris and dust and floods deposit silt and things, and the layers build up.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.